own light, right? And we can see the moon at night, but does the moon...
Hey, this is Cindy, and I'm a junior at Southeastern High School. I love sports, and I just love how physics is in everything that we do.
It's not producing light.
Hey everybody, this is Nicole Nephew. I'm a junior here at Southeastern High School, and I had a great time at CERN, and I'm excited to share what I learned with everybody.
Hello everybody, I'm Jose Bermudez. I'm a junior at Southeastern High School, and I plan to study physics after high school.
The European Organization for Nuclear Research, called CERN, was established in 1954. It is located in Geneva on the border of France and Switzerland, and is a place where physicists from around the world come to do their research. CERN's first accelerator, the 600 MeV synchrocyclotron, or SC, was used to provide beams for pioneering experiments. In 1971, the world's first proton-proton collider, called the Intersecting Storage Rings, or ISR, began operating. The World Wide Web is used by millions of people every day, but few know its origins. It was invented by CERN scientist Tim Berners-Lee in 1990. CERN is home to a museum called the Microcosm, which displays a variety of particle physics topics. Many of the older experiments are part of an outside exhibit called the Microcosm Garden. 1989 was the year when the LEP made its debut. LEP stands for Large Electron Positron Collider, and it is the most powerful accelerator of its kind. Hopewell was one of the 4 massive detectors that observed the collisions. Operating for 11 years, the LEP was disassembled in 2000 to pave way for CERN's newest apparatus, the LHC.
The Large Hadron Collider is a 27-kilometer ring buried underground on the border between Switzerland and France. After the ring begins operations, it is expected to open the world of physics as the world's most powerful particle accelerator. Some of the revelations that are expected to emerge from the LHC are the origins of mass, dark matter, hidden symmetries of the universe, and maybe extra dimensions of space. During activation, the particles will be accelerated at speeds close to that of light, and then collided inside one of the 4 main experiments, the largest of which is ATLAS.
Okay, I'm working on the ATLAS experiment. I'm from Lawrence Berkeley National Laboratory, California, and I've been collaborating with this experiment since the very beginning.
How long has that been?
Since 1993, wow. Which means those were the years of the first studies.
The Higgs particle, also known as the God particle, was the brainchild of particle physicists in the 60s, amongst which are Peter Higgs, Francois Englert, and Robert Brout. Through the theory of the Higgs particle, scientists plan to explain the connection between mass and matter, as well as the interaction of the electromagnetic force and the weak force. Peter Ware Higgs was born May 29, 1929. Now a professor at Edinburgh University, was one of the main theorists behind the idea of an elementary particle field with mass-giving behavior.
Present accelerator and experiments, people have worked more than 15 years to put it together, to do the initial research and development work for the technology developments that would lead to the definition of such a project, and then organizing that the things get agreed upon, financed, and put in place. So it is clear that even if the LHC starts now, we have to start thinking about the future.
The antimatter factory is unique to CERN. No other place in the world studies matter or antimatter as deeply as here.
The reason why we think matter is something special is because it's all around us, and there's no antimatter around us. But if you think back to the moment of the Big Bang, when everything in the universe was condensed in one very small point, this energy then transformed itself into stuff. But if you look out in the universe right now, there is absolutely no antimatter from the moment of the Big Bang. It's all disappeared, whereas all the other stuff is matter from the moment of the Big Bang. And so in a way, this is something that's very embarrassing. We've sort of lost half the universe, and we're trying to find it back here in these experiments.
To make antimatter, around 10 billion protons are smashed at high speeds into a tungsten metal block. When the particles break apart, physicists separate the antiprotons and use them in various experiments. One of these experiments is looking for new ways to treat cancer.
So what we're trying to do is compare the color of the light emitted by hydrogen and the color of the light emitted by antihydrogen, and compare the two. And the precision we want to reach is a number. It's 10 to the minus 18. But to give you an image of what that means, because it's not something that one is confronted with normally, imagine you've got the Mont Blanc over there, big mountain 5 kilometers high. You put it on a balance and you weigh it. And then you put a snowflake on top and you weigh it again. If you can tell the difference between the Mont Blanc and the Mont Blanc with a snowflake on top, that's the precision we're trying to reach here with hydrogen and antihydrogen.
CMS, or the compact muon solenoid, is built in a warehouse above ground before it is taken 100 meters below France. At 12,500 tons, CMS is not as tall as Atlas, but it definitely weighs more. It is designed to detect muons. Physicists believe the Higgs particle will produce muons when it decays. Since its construction began in 1998, over 75,000 dense lead tungstate crystals have been installed. The information these crystals help collect will be sent to a huge network of computers called the grid. The information will then be processed and shared around the world through the internet.
One of the main things that this machine here at CERN is it's a discovery machine. So we're looking to discover new particles, and so the particles that we detect, one of the channels that this new particle could go through, this Higgs particle could go through, is to decay into muon.
Over 1,800 physicists, 150 institutions, and 31 nations have come together to build CMS. ALICE is a large ion collider experiment. The physics department from the University of Houston will continue to contribute to its construction.
So this is the main CERN site. This is the border. This is the crosses. You see how the border cuts through. This is Switzerland, this is France. You see the ring. Now, this is where we are here. This is point 2. This is Alice. We will look both at proton-proton and at lead-lead, and then later there will be other combinations of particles. But this experiment was designed to look at heavy ion. And Susan asked the questions. She said, CMS, Atlas, and Alice are all different. They're not the same kind of detector. And the answer is yes. They're all very different. Each one has been designed to look at the physics from a different angle. Both CMS and Atlas are both principally designed to look for the Higgs. And each one of them has a different philosophy in terms of the kind of things that they would be sensitive to and the kind of resolutions that they would have. Alice has been designed principally to look at heavy ion collisions. So Alice can look at many more particles at the same time, but fewer interactions. CMS and Atlas can look at proton-proton interactions at a huge rate. I mean, they can see 20 interactions about every 40 nanoseconds to 30 nanoseconds, whereas Alice can only take maybe a maximum of around 4,000 per second. But Alice can take a single event with 80,000 tracks in it, whereas the PP events will have maybe 10% of that or less.
I am so excited. So it's been pretty busy and we've seen a lot of exciting stuff. And that's it for now. Hi.
Here we are, guys. Living the night.
Hi, doggy doggy. I'm gonna kill it.
Ready next month as well.
We are now in Building 40 at the CERN area of this place.
The hospital. I guess I'm just gonna where? This is our friend.